This is going to be some quick notes about solving RC circuits. And when we say RC circuits, what we mean is a circuit with a resistor and a capacitor in it. I know that in the hobby world, RC means radio controlled, but here in physics by RC we mean a circuit with a resistor and a capacitor. So if we want to look at a circuit with a resistor and a capacitor, they're pretty simple. You know, you've got a circuit with a resistor and a capacitor, an R and a C. And also notice that we're for the battery, we're using this little script, a script capital E, and that's traditional to use to remind ourselves that instead of, if we're being really formal, we may say battery voltage, but that there's some subtle reasons to refer to it as the EMF instead of the battery voltage. But you know, we'll say battery voltage in speech, but we write it with this script capital E, meaning EMF. And our concern here is going to be the following thing. What happens in this circuit that has a battery, a resistor, and a capacitor? What happens here when we close this switch? What happens to the circuit? How much current flows? How much charge moves? What's the voltage over the resistor? What's the voltage over the capacitor? How does this circuit behave over time when that switch is closed? And the usual assumption, and it's important to mention here because we will be concerned with initial conditions, that at least for our purposes today, we're going to talk about starting this with an initially uncharged capacitor. And so the question is, how do we address this? Well, first, let's think about this conceptually. When we close this switch, current is going to flow. Current's going to flow through this resistor and onto the capacitor. We have an uncharged capacitor, and that the capacitor is going to begin to charge itself up during this process. It's going to charge up, and we're going to get little positives here, little negatives here. Those plates are going to start to get some polarization. But as that happens, that charging process is going to change the dynamics of the rest of the circuit, because once we've got a little bit of a voltage drop right here, that's going to change the voltage drop over the resistor. We could think of this as there being a voltage over the resistor, and then there being a voltage over the capacitor, and there being a battery voltage. And one thing that we know is that all those things have to add up to zero, right? If some charge starts here, that it's gonna go up in potential by going through the battery. There's going to be no change as it goes through this wire. There's going to be a drop in potential as it has work done on it going through it does work going through the resistor. And then from here to here, there's going to be a change in potential because there's an E field that's building up inside of there. And that when we get back to here, we'd better be getting back to the same place. So as we build up potential on the capacitor, that means the potential on the resistor has to be going down. So when the potential on the resistor goes down, that's going to have an effect on the current, because when there's less voltage difference from here to here, when there's less voltage difference there, then there's going to be less current. And when there's less current, that means the rate at which little pluses are coming onto here and piling up on the plate is lower, right? Less current means fewer charges piling up on here. So that means this potential is not building up at the same rate. So as the current falls, the rate at which the capacitor charges up also falls. So what does that look like? What does that look like? It's going to look like this. If the capacitor starts out with zero initial voltage and it starts to charge, so this voltage goes up, but as this voltage goes up, the current falls, right? And as the current falls, as there's less and less current, that means that the rate at which this voltage is rising, that rate of change gets slower. So the current is going to, the voltage is going to go up rather at a decreasing rate. So as the voltage goes up, its rate of increase gets smaller, and it's going to get smaller and smaller and smaller. And then let's think, what's the largest that this voltage could possibly get up to? Well, the largest it could get up to is the battery voltage, because if it charges all the way up until this is charged up to the battery voltage, then no more current is going to flow, and we're going to stop. So this is going to get closer and closer to the battery voltage. We should make that a script E and not an epsilon. Meanwhile, as that's happening, what's happening to the voltage in the resistor? Well, we're going to start out with voltage across the resistor is equal to the battery voltage, and then as the capacitor charges up, then there's going to be less and less voltage across the resistor, because there's less and less, well, two reasons. One, there's less and less current flowing, and we know that the voltage across the resistor is equal to IR. But it's also less and less because as we have voltage across the capacitor, then there's a lower potential difference across the resistor. So let's take a look at how to do this quantitatively, how to work out the equations for this behavior. RC circuits can look like lots of different things. This is your basic capacitor charging setup, but the steps for working out what happens, the steps are the same no matter what. So we're gonna do out this one setup with these 4 steps, and then but you should be able to apply the same steps to everything else. And the steps are that you write a loop rule statement, then in that loop rule statement you rewrite the current as a charge rate and the capacitor voltage in terms of the charge. Then that's going to give us a differential equation, and then we're going to solve the differential equation and then use the initial conditions to get a final charging function. So let's do that. Okay, loop rule statement. Step 1, loop rule statement. 1. What's the loop rule? The loop rule says that if we start at any point and we go around a closed loop in a circuit, that the total changes in potential are going to be 0. Well, what happens here? We're going to go through a battery, and this is the low side of the battery, and this is the high side of the battery. So we're going to go up in potential. We're going to go here. That's not going to be any change. As we go through the resistor, right, there's going to be a drop in potential, because this is the high potential side of the resistor, this is the low potential side of the resistor. So as we go through here, we're going to lose potential. And then once the capacitor starts to gain any charge, it's going to gain positive charge here and negative charge here. So when we go through here, that's also going to be a loss in potential. So how do we write that? We write that by the loop rule statement would say that the battery voltage, or EMF, minus the change in potential over the resistor. And what's the change in potential over the resistor? We use Ohm's law, right? V equals IR. And then minus the voltage across the capacitor. That's going to be equal to 0. Right? And we said that's positive E. Again, that's the EMF is positive because we're going up. That's a positive change in potential. There's no change. This is a negative change in potential from here to here, and this is a negative change in potential. That's why these minus signs are negative. So there's our loop rule statement. Step 2. We're going to rewrite this statement, and it's going to look like this. We get the battery potential, and then this is the important thing to recognize. That current right there, our definition of current is the rate at which charge flows, the number of coulombs per second that are moving. What are those coulombs per second doing? They are going onto this capacitor, right? There's nowhere else for this charge to go, right? There are no other branches. It can't go there. It can't go here. So any charge that moves has to end up on this plate. So we're going to, instead of saying I, we're going to say dq dt. And now we're also going to look at this V sub c. Ultimately, I'm interested in knowing what the voltage of the capacitor is, but notice that I've just added something here. I've just written this in terms of the charge on the capacitor, that dq, and so I'm going to rewrite the voltage also in terms of the charge on the capacitor. How do we do that? Let's see, I remember the definition of capacitance is charge over voltage, and so that means that voltage on the capacitor has to be the charge divided by the capacitance. Okay, so I can say that this last one is the charge on the capacitor divided by the capacitance. So now I've rewritten my equation. We now have a differential equation. And so how do we deal with this differential equation? A couple of things to remember here. We're looking at it. These are a color change. Let's just take a very close look at these. That's a constant, that's a constant, and that's a constant. And then this is a variable, and here's the derivative of our variable. And in fact, what we have here is we've got this function. What we're really saying, that just says q, but we got to remember what we're really talking about is a function q of t. So here we've got an equation that relates a bunch of constants, a charging function, a function that says how much charge is on the capacitor, and the derivative of that function. So here's our differential equation. And remember that differential equations, the only thing that you are responsible for is being able to have a solution and show that it works. And in fact, when we're done solving this differential equation, you'll have a solution. I don't actually recommend that you memorize it, but if you use that solution a bunch, you're going to start to recognize it, and it's totally legitimate to be able to pull that solution out and say, hey, this solves this differential equation. On the other hand, you also really want to know the technique for getting to that solution, because not all capacitor problems are going to look exactly alike. So we're going to go through the solution now, but just to be clear, it's totally okay. Hey, how come you won't scale? Okay, so let's see if we can make this thing work. All right, so let's work on this differential equation. Differential equation. So what we're going to do is we're going to take this thing and we're going to, it's a first order separable differential equation, and so our job is going to be to get, what are the real variables, right? We got a bunch of constants, but the real variables are q and t. So we're going to try to rewrite this so the q's and the t's are completely separate. So I'm going to say the EMF minus q over c is equal to r dq dt, and let's see, I'm going to divide both sides by r, and now what I'm going to do is get the q's and the t's all together with one another like this. I'm going to say dt is equal to dq over EMF over r minus q over rc, and then let's see, maybe we can rewrite that as dt is equal to, if we multiply it on the right hand side by rc, we could get rc dq over EMF times c minus q. Okay. Okay, what do we do with this? Well, if we remember, what we do at this point is we integrate both sides. And so if integrating the left is going to be pretty easy. That's going to be, whoops, come on, baby. Integrating the left is just going to be t plus some kind of constant. And tempted as I am to use c as a constant, we already have a c for capacitance, so I'm going to use k for a constant. Maybe you could use some kind of other c symbol. And then the right-hand side, to integrate this, well, let's see. I'm going to do a u substitution here, and I'm going to say that my u is going to be ec minus q, and my du is going to be equal to negative dq, and so this thing is, integrating that thing is going to be just the integral of negative du over u. Oops, I forgot the RC out front. Sorry this is so messy, but you get the idea. And the integral of this is the ln of u, so it's going to be RC times the ln of u. RC times the ln of u, which is EC minus q. And now I'm going to plus some other constant. Maybe I'm going to call this K2. But by the law of persistent arbitrariness, we can combine these two, and we have just, they're combined together into this one arbitrary constant here. Now, what were we trying to do here again? Remember, what we're looking for is Q is a function of time, so we want to find Q as a function of time. So let's see if we can solve for Q. To get rid of the ln, wait a minute, I'm missing something. The minus sign. I need a minus sign there. Okay, so I'm going to bring the RC over, and so I'm going to get negative T over RC plus K. Wait, don't I have to divide the K by negative RC? Yeah, but this is a new K, and by LOPA it's just K. And the ln of C minus Q. And now I'm going to get rid of the ln by exponentiating both sides. So the exponential of negative T over RC plus K is equal to the EMF times the capacitance minus the charge on the capacitor. Well, we're really getting somewhere now. I can say e to the this thing plus this is the same as e this times e to the k. But what is e to the k? It is also an arbitrary constant. So e to the k is just some arbitrary constant, so I'm going to say k e to the negative t over rc is equal to c minus q. Alright, now we're really getting close. I'm going to kick over the q and kick this over, and we're going to get q, and now I'm going to write it as in functional form. Q is a function of time, is this minus some constant times e to the negative t over rc. Oh, we're almost done. What's the problem? The problem is this k. What is that k? How do we figure that out? Wait a minute, isn't there a last step? Boom, boom, boom. What was that last step? Ah, apply initial conditions. Wow. So we're going to apply the initial conditions. And let's remember that the initial conditions, step 4, initial conditions. The initial conditions say that when the time is equal to 0, that the charge is equal to 0. And so we're gonna plug that into this guy here. So when the charge is equal to 0, and that says this minus k e to the, oh, this whole thing is 0. So this right here, e to the 0, is just 1. So that says that K is equal to the battery voltage times C, which is the same as that first term right here. So now what we're going to get is the following. I hope you're following this. Q as a function of time is equal to the battery voltage times the capacitance times 1 minus e to the negative t over RC, parenthesis. And we originally were asking not what's the charge on the capacitor, but what's the voltage across the capacitor. How do we find the capacitor voltage? Let me see. I always just have to write down the definition of capacitance. C equals Q over V. So the voltage is equal to the charge divided by the capacitance. So if I just take this charge function and divide by capacitance, I should have the voltage function. So the voltage, oh, well, that's easy. I can just divide by the capacitance right there. 1 minus e to the negative t over RC. Cool. Now let's ask if this makes any sense at all. Wow, this is... Man, I still don't understand this program, right? These things are separate. They move around separately. Okay, we'll move them around separately. We'll let them stack up. Go. Well. Okay, you can get small. Wow. Sorry about this. Okay, what do you want for quick unedited? There we go. Okay, so let's make sense out of this guy here. Boom. Let's make sense out of you. Does this make conceptual sense? Well, when time is equal to 0, let's do just a quick check. When time is equal to 0, then this term here is basically equal to 1. What's in the parentheses is basically equal to 0, and so the voltage is 0 at the beginning, which makes good sense because that was one of our requirements. So at the beginning we're going to have 0. What happens when the time gets very big? When the time value gets very big, then this becomes e to some big negative value. So this approaches 0. This right here is going to approach 1, and so what we're going to get close to is the battery's EMF. So what we get is something that exponentially approaches the battery's EMF, which is in line with our conceptual expectations. Let's just talk briefly about the anatomy of this equation. So what we have here is we've got this expression here, which is going to start us out at 0 and then get us closer to 1. What we're getting closer to is the battery potential. And then my question is, what is it? We know we start out at 0, and we know that we end up at the battery potential. What controls the rate at which we do that? I mean, for instance, in this graph, right, we could do it the way it's drawn, but we could also end up there, you know, like that or like that. And the thing that controls that is this guy right here. The denominator, the bottom of the fraction in the exponent there. That RC is what's going to control the rate at which our capacitor charges. And in fact, that product, R times C, is so important, so crucial in this, that we give it a special name. It's called the time constant, and it's written with the Greek letter tau. So when someone talks about the time constant for a capacitor or an RC circuit, the time constant for an RC circuit, what they're saying is the product of the resistance times the capacitance. And the reason it's important is it governs the rate at which the capacitor charges. What does it mean specifically? Like if you say, hey, this thing has a time constant of 2 seconds, by the way, notice it has to come out in seconds because we've got time on the top. The exponent has to come out without dimensions, which tells us, by the way, that ohms times farads has to equal seconds, and that's something worth proving to yourself on the side, that ohms times farads really is seconds. But what do we mean if we say, oh, the time constant is 2? Well, if the time constant is 2 seconds, what we mean is that's the amount of time it takes to get to an exponent here of -1. So the tau is the time to V is equal to -1 over E. And this is some nice, clean, well-established number that I can't remember. It's like 63% or something like that. Work it out yourself. But that's so the time constant tau is roughly the time it takes to charge up 60-odd% of the total ultimate charge. So that's a template for RC circuits. It lets us do a simple charging circuit, right? That's what we just did. What happens when this charges? But you should be able to use exactly those same tools to do things like, oh, what if we have an already charged capacitor and we discharge it, right? You should be able to use that same sequence of events to say, oh, I'm going to start out with some initial Q, and then say, oh, let's just let this capacitor discharge through a resistor. Sometimes that gets set up in a more complicated circuit, kind of like this, so that you could do both things. Right? If this switch is thrown to the left, it's a charging circuit. If that switch is thrown to the right, it's a discharge circuit. And there are lots of variations on this, but that's basically what we're talking about, RC circuits. And steps for an RC circuit, 1, write the loop rule. 2, the current is the rate of change of charge on the capacitor. By the way, that's not, in the one that we did, we talked about the current as if it was the same everywhere. That's true in a single loop circuit. If you've got a more complicated circuit, that's going to be the current in the branch that has the capacitor. And the third thing was solve the differential equation, and the fourth thing is use the initial conditions. It's useful also to think about one big overview aspect of capacitors, just generally how they act. Let's think about the current here. When we know that the current starts out, right? It starts out flowing, and then as the capacitor charges up, and if you don't believe this, you can go back and work it out, but you can do this based on what the voltage is over the capacitor. No, that's not what I meant. You can go back and work this out by what the voltage is over the resistor, because you know that the current is going to be the voltage over the resistor divided by the resistance. That current starts out as just the battery potential divided by the resistance. But as the capacitor charges up, that current falls down to practically zero. And so it's a worthwhile shortcut to think about, particularly if you're looking at more complicated circuits, that for short-term purposes, at the very beginning, for something where the time is really short compared to tau, right, a very small percentage of what the time constant is, how does the capacitor act? Well, it acts just like a wire, right, because we're getting current, we're getting normal current, the current that we would get if there were no capacitor there. So the capacitor, in the very short term, uncharged, just acts like a wire. But at the long term, where the time is much, much greater than tau, then it's much, much less than tau. When the time is much, much greater than tau, basically we get no current down here. And so after a long time, when the capacitor is really charged up, well, when it's really charged up, it's not going to charge up anymore. So this acts like a broken wire. So that's a nice shortcut if you're looking at a more complicated circuit and you're trying to visualize what's going on with the capacitor. It's useful to go, oh, beginning capacitor is like a wire, ending capacitor is like a broken wire. And I think you'll find this even more useful when later on we compare this to inductors. But that's about it. That's RC circuits for you in a very short and messy version.